Good afternoon. I am Leontin Padurariu. I am researcher at Alexandru Cuza University of Iași, Romania, and I belong to the Faculty of Physics and the group of dielectrics, ferroelectrics, and multiferroics. I would like to thank the organizers for the invitation to share our newest results to the International Conference on Material Science and Nanotechnology, and I am honored to be the first speaker of a very interesting session of the conference. In our group, we are currently working on numerous topics like composites, porous materials, materials for tunability, polymer-based composites, but today I have decided to present an aspect of barium titanate ceramics that intrigued our attention because it was scarcely reported in literature before, but we consider it has a great potential impact on the functional properties. My presentation will be a mostly theoretical one, but completed with enough experimental confirmations, and the main aspect that I will discuss too is related to the phase superpositions. This is the content of my presentation. I will start with a short introduction about crystal structures in barium titanate and its base solid solutions, and I will continue with the presentation of the modeling approach based on Landau-Devonshire theory, which led us to the idea of phase superpositions in barium titanate-based ceramics. In this part, I will discuss mostly two aspects: phase coexistence in unpoled ceramics and field-induced phase transitions. Although the main ideas presented in this work can be considered general for all ferroelectric ceramics, I present the results for pure barium titanate and barium titanate substituted with 5% tin in titanium positions, systems that were also investigated experimentally in details in our group. After presentation of the experimental comparisons, I will present other more recent results that show methods to tailor phase superpositions as grain size reduction and porosity. I will finish my talk with conclusions, and I will present some perspectives and future works. The four structural phases of barium titanate are very well known in literature. Above 120 degrees Celsius, barium titanate is in cubic phase, and the titanium ions are not shifted from the center of the unit cells. Below this temperature, towards 5 degrees Celsius, barium titanate is in tetragonal phase, which is characterized by a shift of the titanium ions along 1,0,0 direction and equivalent axis. Between 5 degrees Celsius and minus 90 degrees Celsius, barium titanate is characterized by an orthorhombic phase and the polarization orientation along 1,1,0 direction and equivalent directions. The fourth possible state of barium titanate is rhomboidal, which usually appears at temperatures below minus 90 degrees Celsius, and it is characterized by a polarization along 1,1,1 direction. Therefore, at some temperatures, barium titanate suffers phase transitions, which are important, interesting to be studied because they are usually accompanied by enhancements of the functional properties like dielectric constant, as shown in this graph, but also piezoelectric, pyroelectric, electrocaloric, and many other properties. Among the three structural phase transitions, perhaps the most interesting and promising to be studied is the orthorhombic to tetragonal phase transition because it is very close to the room temperature. But unfortunately, we consider that this phase transition is not sufficiently investigated so far. The methods to modify the temperatures of phase transitions in barium titanate is to substitute some of the titanium ions with other metal ions which are not shifted from the center of the unit cell. Metal ions could be zirconium, tin, cerium, hafnium, but their presence induces similar phase modifications as shown in these phase diagrams. When increasing the substitution degree with metal ions, we observe an increase of the transition temperatures for rhombohedral to orthorhombic and orthorhombic to tetragonal phase transition, and a reduction of the tetragonal to cubic phase transition. In addition, the phase diagrams show that there is a region in which all four phases might coexist. That is a quadruple point. However, many of these aspects accepted in literature are derived from the studies of single crystals. Ceramic materials are more complex than single crystals with complex domain structures and random rotations of the grains and orientations of the polarizations. Therefore, we propose to check if structural phase transitions are sharp and they occur indeed at a certain temperature, or it is more realistic to consider that phase transitions are produced in a range of temperatures for which at least two phases might coexist. The most facile way to describe phase transitions in barium titanate-based ceramics is to employ Landau theory. We use the sixth order expansion of the free energy in which alpha parameters are dependent on temperature and substitution degree x. In fact, alpha parameters were calculated as linear combinations between the parameters for pure barium titanate, very well studied in literature, and parameters corresponding to x equal 0.12, for which a quadruple point was reported in tin-doped barium titanate ceramics at 40 degrees Celsius. In particular, for x equal to 0, the case of pure barium titanate, the parameters are very close to the ones proposed by Bell and Cross for single crystals. For x equals 0.12, we wanted to obtain a quadruple point, as shown in the work of Ioan et al., and in order to describe a quadruple point. And for this, the free energy should be transformed in a much simpler expression like the highlighted one on the slide, for a temperature of 40 degrees Celsius. In these images, the diagrams of the free energies are presented as dependent on two components of the polarization, P1 and P2, while the third one is considered equal to 0 for the simplicity of the representation. In the absence of an external electric field, we can observe that both systems present stable orthorhombic and tetragonal phase, but with lower energy values in tetragonal phase for pure barium titanate and lower energy values in the orthorhombic phase for solid solutions. When dealing with Landau theory, many authors interpreted the diagram as the first one as corresponding to a tetragonal phase, because the minimum of energy is established in this state. Similarly, in the doped barium titanate, the absolute minimum of energy is an orthorhombic phase. However, at a deeper look, we can see that both phases are in stable minimum of energy, and this diagram already leads us to the idea of phase coexistence in complex systems like ceramics. The next diagrams correspond to an electric field applied along 110 direction, which favors the minimum of energy in orthorhombic phase, both in doped and in pure barium titanate, and to an electric field oriented along 100 direction, which makes tetragonal phase more stable. In fact, these diagrams show the modification of the free energy during a phase transition. In complex ceramics, all orientations of the electric fields are possible. In order to derive some quantitative information about the concentration of the phases at different temperatures and compositions, we employ the simple Monte Carlo algorithm. The algorithm consists in successive and small modifications of the polarization of the grains until a stable minimum of energy is reached. The procedure starts from a random configuration of the polarization of the grains. As expected, many grains relax in the tetragonal phase, which is characterized by the lowest energy in this example. However, other grains relaxing the orthorhombic phase, which is also a stable minimum of energy. Using this procedure for 10,000 grays, we are able to estimate the concentration of the phases in equilibrium state. The phase concentrations were computed for three systems: pure undoped barium titanate, tin doped barium titanate with 5%, and tin doped barium titanate with 12%. The first graph showed that even undoped barium titanate is characterized by a large temperature range of phase coexistence, around what are considered by many as transition points. Accordingly to this graph, the orthorhombic and tetragonal phases coexist from minus 10 degrees Celsius to 30 degrees Celsius. The rhomboidal phase is present towards minus 20 degrees Celsius, and the orthorhombic phase do not vanish at minus 90 degrees Celsius. Even tetragonal to cubic phase transition do not occur at a single temperature value, but is characterized by a range of transitions. The Landau approach describes correctly the shift of the transition temperatures in tin doped barium titanate and describes the quadruple point for x equals 0.12. The general conclusion derived from these graphs are that phase transitions are produced in a range of temperatures and not at a single value. In order to describe the field-induced phase transitions in ferroelectric ceramics, we have to take into consideration the random orientation of the grains. Therefore, we improve the previously described algorithm with following steps. For each grain, random orientations of the crystallographic axis are generated. The component of the electric fields on the crystallographic axis are then computed and introduced in the Monte Carlo algorithm to obtain the components of the polarization on the crystallographic axis. After that, the component of the polarizations are then calculated for each grain on the reference axis, which are in fact the measurement axis. Finally, the macroscopic polarization is computed as an average of PZ component of each grain. And this procedure is repeated for different values of the external applied electric field. In this graph, the first polarization curves that corresponds to a poling process are represented for unpoled and poled barium titanate, doped and undoped. Both samples present phase superpositions at room temperatures, which was considered 23 degrees Celsius. The orthorhombic phase is favored in solid solutions, and therefore the polarization values are generally higher. Although both tetragonal to orthorhombic and orthorhombic to tetragonal phase transitions of the grains are possible depending on the grain rotations, as discussed before, we can observe that overall the tetragonal to orthorhombic field-induced phase transition is favored. This can be explained by the fact that the orthorhombic phase has 12 possible orientations and not only 6 like the tetragonal phase. Very interesting is the fact that the amount of the phases do not change monotonously, but it presents peculiar concentrations at intermediate field values. For example, the minimum amount of the orthorhombic phase in undoped barium titanate is obtained for 10 kilovolts per centimeters, that is 29%, while the highest concentration in doped barium titanate, 94th percentage of orthorhombic phase, is obtained at 12 kilovolts per centimeter. The two investigated systems for comparison with the theory results are dense ceramics of pure barium titanate and doped barium titanate with 5% tin substitution on the titanium position. The samples were prepared by solid-state reaction. The scanning electron microscopy investigations demonstrated that the samples have good densities and high grain size, thus not being affected by the porosity or grain size effects. The permittivity versus temperature measurements show that the samples are good dielectrics with tangent loss less than 5% in the entire temperature range from minus 150 degrees Celsius to 150 degrees Celsius. The transition temperatures are characterized by maximum values of the permittivity respecting the general trends described by the Landau theory as increase of the rhomboidal to orthorhombic and orthorhombic to tetragonal phase transitions and decrease of the Curie temperature in solid solutions. Like in the modeling predictions, the hysteresis loops measurements demonstrated that the saturation and Ramanen polarizations are higher in the doped barium titanate than in the pure barium titanate because it is dominated by the orthorhombic phase. Very remarkable is the comparison between the first polarization curves determined by the experiment and predicted by the calculations. The doped barium titanate presents more rapid increase of the polarization at low applied field values, but better saturation at high applied fields. Unfortunately, the peculiar values of the concentration of the phases at intermediate applied fields could not be demonstrated yet by experiments. However, we are able to analyze the phase superpositions in unpoled and poled samples by X-ray diffractometry and Rietveld refinement. The increase of the orthorhombic amount during polling towards 25 kilovolts per centimeters can be highlighted at a qualitative level by the two peaks at 45 degrees corresponding to the tetragonal phase, the other one to orthorhombic phase. The Rietveld calculation results are in agreement, at least at a qualitative level, with the predictions of the models. Both types of systems are characterized by phase superpositions in unpoled state, and the amount of the orthorhombic phase increases after polling towards 25 kilovolts per centimeters, with higher amount of the orthorhombic phase in the solid solutions. These two experimental cases were a good start in confirmation of the hypothesis regarding phase superpositions and their impact on ceramic properties. In the following, I would like to present other more recent results regarding the possibility to adjust further the phase superpositions in barium titanate-based ceramics. For example, it was reported in literature that the reduction of grain size modifies the alpha-1 and alpha-1,2 parameters, which significantly change the diagrams of the free energy. For example, in these 3D diagrams, we can notice that close to room temperature, both tetragonal and orthorhombic phases present stable minimum of energy, but a coarse ceramic is predominantly in tetragonal phase, while a fine ceramic is predominantly in orthorhombic phase. In fact, phase superpositions exist at even lower temperature values, but between orthorhombic and rhomboidal phases. These diagrams are useful to describe the appearance of phase superpositions in barium titanate with various grain sizes, but the Monte Carlo algorithm was further applied to derive qualitatively the amount of the phases at various temperatures and grain sizes. Therefore, we have proposed a more generalized phase diagrams by comparison with the diagram proposed before in literature. In fact, this diagram was initially proposed in literature by other authors, but without the color scale and excluding the possibility of phase coexistence. In other words, assuming sharp transition of the phases. We consider that this diagram explains the discrepancies between the experimental results proposed in literature by many authors working with similar samples. The best collection of the results that were reported in literature are presented in the cited article. Another method is to intentionally introduce local stress strain, preferable shear stress by defects or dislocation, as we recently presented in this work. One major advantage of Landau-Devonshire theory is that it can take into consideration the role of local stress as shown in literature before and by us in a recent paper. The application of a moderate shear stress favors a stable and well-defined minimum of energy in orthorhombic phase. In addition, the orthorhombic phase formation can be further facilitated by the application of an external electric field. In our group, barium titanate powders with local defects and dislocations were used to prepare porous barium titanate ceramics with various porosity levels from 4% to 26%. In these samples, porosity helped release the internal stress, and therefore we obtained samples with predominant orthorhombic phase in dense ceramics and tetragonal phase in porous structures, as shown by XRD analysis. The local stress and phase superpositions had a major impact on the nonlinear dielectric properties. If for porous structures, the dependence of permittivity versus applied electric field show a typical Johnson-like shape, the dependence of permittivity versus field is peculiar at low porosity level. In other words, the dependence show a strong hysteretic behavior, unexpected by comparison with the results presented in literature before. The Landau-Devonshire theory proved to be very useful to describe these peculiar results, but in combination with finite element method for the estimation of the local electric fields. As expected, the amount of the orthorhombic phase increases when increasing the average shear stress in unpoled ceramics, but the concentration of the orthorhombic phase show a peculiar dependence on the applied electric field. The orthorhombic phase show a maximum at intermediate field values, while the tetragonal phase present a reentrance at higher field values, while at maximum field values, the orthorhombic phase amount increases again. The major conclusion of this work is that in ferroelectric ceramic, the structural phase transitions are produced in a relatively large temperature range and not at a single temperature value. The orthorhombic phase is in generally favored by the application of an external electric field, but the orthorhombic to tetragonal phase transition is also possible. The orthorhombic phase is very important because it presents 12 possible orientations, more than the tetragonal and rhomboedral phases. It is characterized by the highest polarization, which is a beneficial factor for increasing tunability, piezoelectric, pyroelectric, and functional properties in general. And another interesting fact shown in this work is that the maximum of the orthorhombic phase is not necessarily obtained at the highest applied field, but rather at intermediate field values. And this aspect deserves to be further investigated in polling experiment. Another interesting and promising aspect is that phase superposition could potentially be controlled in the future by preparing samples that synergically combine the effects of substitutions with metal ions, grain size reduction, introduction of local stress or strain, and porosity effects. In the end, I would like to thank to this Romanian project that supported our research, and I would like to thank you for your attention.